Thank you for giving me this opportunity of this invited talk. So I'm going to present results that have been obtained by the SMOS L'Océan group in the L'Océan laboratory and in collaboration with people from IFREMER, the LPO laboratory, the team of Fabienne Gaillard, and this has made in collaboration also with people from Lagos IRD, both in Toulouse and Nouméa. So, as mentioned this morning by Merrick Strokosh, and also the results you show presented by Jordi and others, the SMOS salinity at global scale looks pretty in good agreement with the one derived by optimal interpolations derived from in situ data, as you can see here, for 3 months in boreal summer in 2010. So the spatial variability at first order is well reproduced, and the objective of these talks is to look in more details at the comparisons between SMOS salinity and Argo and in situ sea surface salinity. First, I will give some indication of large-scale comparisons, and then I will focus on what happens in the tropics, look at the rain impact, and look at the 2011 minus 2010 interannual variability. So, about the data and the method we used the SMOS sea surface salinity retrieved with the ESA version 5 reprocessing during the years 2010 and 2011. I recall that the sea surface salinity measured at L-band is representative of the first centimeter depth, and in this talk we consider high resolution SMOS data at 40 kilometer resolution, or averaged over 1 degree, 10 days, or 1 month, as derived in this paper. We also used the rain rate, the satellite rain rate, derived by the remote sensing system, and we collocate them within about plus or minus 1 hour with the SMOS salinities. Concerning in situ salinity, we use both Argo individual profiles provided by Coriolis, and what we call the sea surface salinity in that case is the upper salinity taken between 10 meter and 4 meter depth. We use also interpolated sea surface salinity maps derived using the in situ analysis system at IFREMER and LPO. And we use also some data from the sea surface autonomous drifter that was deployed in the tropical Pacific Ocean from our colleague at Nouméa IRD. So this is here a comparison of SMOS and Argo salinity during 3 months in 2010. And in that case, we averaged SMOS salinity within 100 kilometers and 10 days around the Argo sea surface salinity. We consider here 3 zones, one between minus 45 to plus 45 north, and 2 other zones that I will detail afterwards. Concerning the large zone, you see the statistics of the comparison. Here it is considering ascending and descending passes. You see the standard deviation of the difference, 0.46 salinity units, and a slight negative bias, which is due to the fact that in that comparison we did not sorted out the data close to the large land masses, and we know that there is negative bias around these places. So then we decided to concentrate on the smaller regions far away for large land masses, and here I present 2 comparisons, one done in the SPURS regions in the subtropical Atlantic Ocean, and one in the northeast tropical Pacific Ocean that contains the ITCZ region. So if you look at the comparison concerning the standard deviation, you can see that the standard deviation of the difference is slightly smaller in the subtropical Atlantic, a non-rainy region, than in the northeast tropical Pacific. And concerning the bias, it is more negative in the northeast tropical Pacific than in the subtropical Atlantic. So the question arises, Why is it like that? Is it this increasing noise can be explained by the effect of rain? And is it the more negative bias in the rainy region could be an effect of rain? So before doing some more statistics, we come back to individual Argo profile, and we have, by chance, one Argo profiler that was collocated with SMOS, collocated with rain rate twice at 10 days interval. So this is here the salinity profile between 5 meters and 200 meter depth. In blue, this is the Argo salinity. And you can see a strong gradient right at the surface because this salinity profile was taken at a time when the float was close to large rain cells. In red here, I have drawn the mean SMOS salinity averaged over 10 days, collocated from collocated measurements, collocated SMOS measurements with Argo. And here you see the two SMOS salinities measured 5 days apart that were collocated with this Argo profile and which participates to this average. This one was taken 6 hours before the Argo profile, and it corresponds to a situation when, again, the measurement was close to a big rain cells, and so we see again very fresh salinity. 5 days after, the other SMOS measurements was taken in a non-rainy region, and we think that the saltier water seen by these measurements is due to the fact that it was in a less rainy region. We did the same exercise 10 days after, so this is the Argo measurements 10 days after. This time, the Argo profile is in a non-rainy region, and you see the difference in salinity, 0.7. The salinity is 0.7 saltier because of the variability, temporal variability, due to the rainy events. And again, SMOS salinity data are quite close to the Argo profiler, except that a few days after the Argo profile, again there was rain, and then the SMOS data become fresher. So this is an illustration of the variability. This is not a demonstration, but nevertheless, it can explain why, when looking at averages over 10 days, we expect more noise on Argo SMOS salinity comparisons in rainy regions. But nevertheless, we also see a negative bias, and this negative bias, we wanted to analyze it in more detail. And so we look again at our SMOS minus Argo salinity comparisons, but this time without any temporal averaging on SMOS data. And here you see the statistic, the mean bias, the standard deviation of the difference, and the skewness of the difference distribution when taking all the collocation in the tropical Pacific Ocean in these rainy regions, or when selecting only non-rainy conditions on SMOS salinity. When doing this selection of non-rainy SMOS points, you can see that we decrease the difference. The difference is less negative because we exclude the rainy data. We decrease also the standard deviation of the difference, which becomes very close to the one that we obtained doing the same exercise over the SPURS region, and the skewness also becomes very close to 0. So this is encouraging because it means that without rain conditions, SMOS becomes very close to Argo, but nevertheless it raises a question. Because when we do such comparisons, we should have also Argo measurements taken under rainy conditions. So I would expect, in fact, that here the skewness should change. It should not be 0 because there should be also Argo salinity data taken under rainy conditions. So there is still an issue, and we anticipate that there could be 2 reasons for that. either that the salinity is fresher at 1 centimeter depth than at 5 meter depth in rainy regions, and we already observed from in situ measurements that it is the case. And the other thing is that there is an Argo undersampling of rainy conditions, and as mentioned by others this morning, the Argo sampling is not perfect. So now I'm going to look in more detail at the 2011 minus 2010 sea surface salinity variability, and I will show that some features are also related to the rain impact. In fact, with SMOS, we sampled the 2010 year, which was the strong La Niña year, at least for the second part of the year, and this will be more detailed in the talk of Joachim Balabrera given by Jordi after that. And here you can see the contrast in July between the 2 years, with very large contrast, corresponding to displacements of the SPCZ and the ITCZ region. Here on the in situ analyzed salinity, and here on SMOS data. And you can see that at first order, we see the same patterns. And similar in November, you can see that similar patterns are seen. But when you're looking at monthly anomalies like that, we always saw that the extrema, like this positive anomaly here, are stronger on SMOS than on the in situ analyzed data. So we look in more detail to that, and in the rest of my talks, I will concentrate in 2 regions. First in the ITCZ region, the one I looked already, and then to a larger region over the South Pacific and Indian Ocean. So concerning the northeast tropical Pacific Ocean, again you see the salinity anomaly from in situ analyzed optimal interpolation, and here the same obtained from SMOS, and here is a scatter plot showing the SMOS salinity anomaly versus the ISAS salinity anomaly. And you see very well that the very positive anomaly are more positive for SMOS and more positive for SMOS. And then we look at the reason for that, and the reason for that is that in 2010, the rainy region appears more fresher, and the extent of the fresher region as seen on SMOS extends further west than seen on ISAS data. So we look at the in situ measurements that were used to build these maps. And here, on this map here, all the black points indicates the measurements that has been used to in the interpolation. And when looking at that, you can see, for instance, that for this very low salinity region here, there is no Argo floats in that region. You can see also very small, almost no measurements in the west constraining this interpolation. Now I come to do the same exercise in the southern region. Again, here you have the scatter plots of the anomaly, and you can see that very positive anomaly are more positive on SMOS, negative anomaly are more negative on SMOS also. And when looking at the positive anomalies in this region, we see that they are more positive, again, because the salinity from SMOS are fresher in July 2010 than the optimal interpolated maps taken from ISAS. But you can see also that there is a very small number of floats in that region. So by chance, we had a float in that region that makes measurements at 45 centimeters from the surface. And you can see here the measurements of the float showing large freshening together with the ISAS in red and the SMOS in blue. And it's very difficult right now to say which one is the best, but clearly ISAS estimates are in the upper values. So this is the summary. So the precision in tropical, subtropical regions right now of SMOS data is on this order of 0.25, 0.3, 0.5, between 45 south and 45 north. At first order, we saw the strong interannual variability we see are consistent with Argo anomaly, but we see more contrasted anomalies, and there may be two reasons for that: a surface stratification effect and an Argo undersampling effect. But anyway, this SMOS salinity appears to be very complementary to Argo profiles.
Thank you, Jacqueline. We'll give you time for just one quick question, but we are running a little bit behind. So one question? Any? Fred.
What do you mean by Argo undersampling of rain events?
Well, it appears that in the map I showed, for instance, on this map, if you look at the fresh region here, you can see that there were a very small number of Argo floats in that region. Maybe it's due to the Probably it's due to the circulation in this area that makes the Argo floats quite rare.
All right, thank you. All right, we do have to move on now to the next speaker. The next speaker is another invited presentation. This is by Ray Schmidt, and he's going to talk about the SPURS program, an overview of the salinity process upper ocean regional study, first results. Let me get you queued up here. What do I need to get to the rest of the... All right, I need help here. I need help. How do I get out of this? Go up one. That's what I just did, I think. Here we go. There we are. Okay, Ray, on your way.
Thank you, Gary. We got off the NOAA about 7 weeks ago, so this is kind of a quick overview of what we accomplished in the deployment cruise for SPURS. Where's the? How do I push the button here? Yeah. Now our motivation, of course, is the global water cycle. Most of the global water cycle is over the ocean, and we believe that salinity is probably the best indicator of change in the global water cycle. The map of evaporation minus precipitation on the top and global surface salinity on the bottom. In the Atlantic, E minus P on the left, surface salinity on the right, and we decided to focus our attention on the salinity maximum at about 25 north, 38 west for SPURS. The idea is we got to understand what the ocean's doing to the salinity field before we can fully understand what changes in surface salinity mean for changes in the water cycle. So here's our study site. We left Woods Hole on September 6th and long steam out to our salinity maximum, and then we returned to the Azores. The idea behind SPURS was to sort of goes back to the old cage ideas. Let's instrument the ocean as well as we can with as much autonomous instrumentation that we're now blessed with as we can get in the water. So we have a lot of gliders, buoys, floats, you name it. We put it in there. Here's our research vessel, NOR, and of course we did CTDs, we did microstructure profiles, we had an underway CTD that we used. We were chased around by 4 hurricanes, made for an interesting cruise logistics sometimes. We managed to get out ahead of the first one, Leslie, and Michael moved out of our way as we got close to the area. Then Nadine sat north of us for much of the cruise. And it was rather interesting. The circulation of Nadine canceled out the normal trade winds, since we had pretty light winds for most of the cruise. And then at the end of the cruise, Oscar sort of chased us, came through right over us and chased us into the Azores. We've deployed a surface flux mooring, Tom Farrar of Woods Hole, We deployed a couple of very interesting crawler moorings from NOAA, from Billy Kessler's group. These are profiling CTDs. That's what a crawling profiler. Interesting ratcheting mechanism, uses the motion of the waves to drive the instrument up, and then it free falls and makes a profile and telemeters the data in real time. We deployed surface drifters, Argo floats, specially equipped Argo floats, which you'll hear about in the next talk, a Lagrangian surface mixed layer drifter, a number of different gliders, turbulence-equipped gliders, deep diving sea gliders, a robotic propeller-driven instrument to look at the upper ocean. Dave Frattantoni deployed what's called a wave glider, interesting new technology. A surfboard is pulled along by a subsurface vane that the relative motion of the waves between the surface and this feature down at about 5 meters depth pulls it along quite nicely at about 1 or 2 knots. Here's a thermosalinograph record from the cruise, and I find this quite striking and quite an interesting observation. When we got into the salinity maximum, it was approaching 37.8 in salinity, much higher than I had expected. And when we got there, it was as if we had saturated an amplifier. And around the salinity maximum, as we surveyed in and out of it, you could see what you might expect to be the signs of random eddy stirring out of this maximum. But within the maximum, it tended to get up to this high salinity and stay there. It was rather surprising to me. And it was also quite surprising that it was as high as we found it to be. We have a lot of CTD profiles. These go to quite deep, but within this salinity maximum, there was a good 50 to 60 meter thick mix layer. Here's some data from the crawler moorings. We see the salinity maximum is right at the surface, so we found the surface outcrop of the salinity maximum. And later on in the cruise, this is one of the earliest profiles is a later profile from the other mooring. You can see freshwater starting to encroach. Freshwater moved up from the south right at the surface towards the end of the cruise. We did a lot of repeat, over 760 profiles with an underway CTD, and here's part of our survey pattern and the upper ocean salinity data as recorded by the underway CTD. We had a lot of calm weather, as I mentioned. Here's the CTD going in on a pretty calm day. But notice there's clouds in the sky, and there was clearly evaporation going on, even with near zero wind speed. And it makes you wonder about the bulk formula, whether it's really accurately estimating evaporation in such situations. And the wave glider temperature and salinity data, just a TS diagram from the wave glider. There's not a strong slope, but you see those afternoons when diurnal warming ramped the temperature up several degrees. There's also a slight increase in salinity, not a strong one, but ever so slight. And when we tried to sample for surface salinities, those were the highest salinities we would observe. Here's a upper ocean structure over 2 days from one of the gliders, the turbulence glider. It's making pretty frequent repeat profiles. This is the upper 10 meters. Here's one of these diurnal warm events in the afternoon, and that's see when we're getting the highest salinity. The data from the EcoMapper was interesting. That's the propeller-driven profiler that Dave Frattantoni was operating. We were on maintaining station with dynamic positioning. Here's the ship right here. And Dave ran it out about a kilometer or so from the ship, and he was sampling one of these diurnal warm layers one afternoon, but notice when he gets near the ship, the temperature drops. So it was clear that the operation, the ship's thrusters, was stirring the local patch of water a few hundred meters around the ship, whereas diurnal warming had built up a nice stratification away from the ship. Here's during the day, you can see the stratification build up in the upper couple of meters. Another thing Dave observed in this stable surface boundary layer are internal waves. Here's a survey he had done with the EcoMapper, and you can see patches of warm and cool water moving through. So there's quite a bit going on in the stable surface boundary layer that's turned out to be quite interesting. We had Fred Bingham along on the cruise, and Fred was getting data both from the JPL group on shore and pulling all the data sets we had out there. We deployed a number of salinity sensing drifters, and we're doing these surveys. So here's an SSF map from one. Well, that covers a fair bit of time, but we deployed the moorings in this area and surveyed there for a while, and then we found that our highest salinity patch was moving to the north, and we followed it north and surveyed it up there. There's certainly an effort to pull all this data together. Here's just a big diagram showing all the components. And we had a group, the dry team, working at JPL, trying to help us with our situational awareness. And we were getting data from their model that was assimilating our data, our salinity data in real time, and in a day or two later we would get an update on an estimate of where the high salinity patches were moving. Of course, one of their big inputs is altimetric data, and you can see there was a high to the east of us and a low to the west, and we found that things were indeed moving to the north, and so we had to follow our salty patch to the north. We were also getting some high-resolution Aquarius data from Nikolai Maximenko at University of Hawaii, and this was actually produced as we were just started the cruise, and it was showing a 37.8 salinity in our target area, and I frankly didn't believe it. I had always thought that the salinity maximum in the Atlantic was 37.3, and but then we got out there and found that it was in fact 37.8. We had a little outreach during the cruise. Eric Lindstrom maintained a blog, and during our cruise, the Navy declared that the replacement for the NOAA is to be named the Neil Armstrong. So that sort of motivated us to put in a phone call with the International Space Station. There's Eric, the captain, and myself talking to the Commander Sonny Williams on the space station. What's been going on since then? Of course, it's only been a couple of months. Here's, let's see, the precipitation rate from the flux mooring, and then surface salinity at the further, just about a 1 meter depth on the mooring. And you can see a good rain patch. Actually, I think that's Oscar. As we left the area, we got a lot of rain from Oscar, and you can see the salinity falling. Then. You can go on the web to the JPL site and see what's going on. This is a map from a few days ago. This is sort of large view. Zooming in a bit, you can see the array. We have the gliders, the UW gliders, performing a large box, and then a butterfly in here. The wave gliders are steaming around pretty frequently, and there's a number of drifters and Argo floats, which you'll hear about in the next talk. we think we may have a record high salinity. Eric did a survey. The only other the highest value at the surface posted in the NODC archives is 37.75. We have an SS bottle sample over 37.8, and some of our instruments recorded even higher surface salinities. So if we do have a new record high salinity for the salinity maximum in the Atlantic, it's very consistent with the work that Paul Dirac's been doing in intensification of the water cycle. Salty areas getting saltier, fresh areas getting fresher. So we successfully deployed our sampling array. All the systems are working well. The surveys revealed very high surface salinity and possibly a record. And this interesting feature of the salinity maximum, it's a hard limited high with the appearance of a distinct well-mixed core in contrast to the eddy-stirred salinity fronts found nearby. I mean, you can understand that with convection, maintaining the evaporation is going to leave salt behind, it's going to convect, and so you can understand why it's well mixed vertically, but what maintains the horizontal stirring within this high salty core? I think we've got some work to do there. As I mentioned, this high salinity reinforces the salinity trends identified by Dirac and Wafels, and it suggests that there is indeed a substantial intensification of the water cycle going on. The next steps, we have a two-ship survey in the spring, March, April 2013, the U.S. ship Endeavor and the Spanish ship, the Sarmiento de Gombo. And the goal is to maintain the glider array, service our instruments, and survey late winter conditions. And then in the fall of 2013, we'll recover all the moorings and gliders that we left out there. So that's the status of SPURS right now. Thanks very much.
We do have time for a couple of questions.
I missed the point. Was the stratification stable or unstable? Is that high salinity surface?
Well, it varied day to day. On a calm afternoon, you would have a surface stable boundary layer of a few meters thick. The temperature would be 2 or even 3 degrees warmer than done 5 or 10 meters. But at night, that would convect and overturn.
One from Eric in the back.
Just an advertisement. We have the SPURS movie on the NASA Hyperwall Tuesday morning at 10:20 and Thursday morning. Giving a little overview.
Oh, is that the one with the time-lapse deployments?
Yeah, the Bostano.
Okay, great. It's great fun, folks. Right. You should catch it.
Yeah. In case you don't know, the NASA Hyperwall is going to be over in the exhibition region. I don't know exactly where it is, but it's worth a look. There's a lot of good information on there. So thank you very much. Right, now it's time to move on to the next talk, and this is given by Jesse Anderson from the University of Washington. Near-surface observations of temperature and salinity from profiling floats, the diurnal cycle, precipitation, and mixing. Now it's going to take me a minute to get us out of here. Get back to your presentation. What did I do the last time? Oh, I went this way. Okay. All right, it's all yours.
All right. And just use the mouse to change or the
You can use that. You can use either
Okay.
one.
Okay. Sweet. All right, so as Gary mentioned, today I'm going to be presenting work that I've been doing with Steve Reiser at the University of Washington, looking at the near-surface observations of temperature and salinity from profiling floats. So generally speaking, we've kind of had a poor understanding of ocean salinity, primarily due to a marked lack of high-quality data at the spatial and temporal resolution needed to accurately characterize it. So the network of 3,600 Argo floats has greatly enhanced our understanding of ocean salinity over the past 20 years. However, they quit collecting data at about 4 meters below the sea surface to ensure their stability over long periods of time. The Aquarius data is going to continue to enhance our understanding of ocean salinity. However, it senses only the uppermost centimeter of the ocean. We therefore have a need for accurate near-surface salinity data so that we can connect Aquarius to Argo, which has kind of been mentioned in the previous talks. So in addition to the larger scale variability that Aquarius and Argo see, we also know that ocean salinity varies at much, much smaller spatial and time scales. A classic example of this can be found in Price's 1979 paper, where he saw the freshening of the water column of 0.15 PSU in the upper meters of the ocean, which was then quickly mixed down to depths of 25 meters in under a day. So in order to look at these smaller scale variability in time and space, we've employed the use of Argo floats, which are equipped with an auxiliary surface temperature and salinity sensor manufactured by Seabird. This auxiliary CTD is unpumped and has an accuracy of 0.05 degrees C and 0.05 PSU and is capable of making measurements of about 5 centimeters in the vertical. Shown here is a typical Argo end cap, which shows both the primary CTD in the back here and the auxiliary STS CTD in white in front. In addition, these floats use iridium telemetry, so we can actually have two-way communication with the floats after we deploy them. Typical Argo floats take a measurement from 2,000 meters to the surface every 10 days. With these, we can actually change that so that they cycle just in the upper 150 meters at 2.5 hour intervals. So shown here is a typical profile from an STS float. We can see from depths of about 2,000 meters to 1,000, it operates as a standard Argo float with only the primary sensor collecting data. At a depth of about 1,000 meters, though, the secondary STS sensor kicks on, and the two operate in tandem for about 30 meters, which results in 120 overlap samples. The reason for this overlap period is it's expected that the STS sensor may drift with time, so we can use this deep overlap to correct that to the known stable primary SBE41 unit. After this deep overlap period, the secondary CTD pump turns off and both operate in only the primary unit collects data until a depth of about 30 meters. So zooming in here to the upper 30 meters, we can see both operate in tandem until a depth of about 5 meters below the ocean surface, at which point the STS unit continues operating and the primary unit turns off. It's important to note that in the upper 30 meters, the ascent rate of the float slows down so that we have a higher vertical resolution of about 10 centimeters. So to date, we've deployed 58 STS units. We primarily began deploying them in the tropical Pacific, since this is where Aquarius sensitivity is highest. But we've also deployed them in the Indian Ocean on both sides of the peninsula, near Hawaii, and then most recently, 24 new floats in the SPURS region. The red dots on here indicate 7 floats which we have changed the mission so that they operate just in the upper 150 meters for 3 weeks. So before I'm going to spend the majority of my time talking about float 6117 and then show some initial results from the SPURS floats. Before I do that, I wanted to show differences for the 31 floats deployed prior to SPURS. So shown here is the difference from the shallowest STS reading in 4 meters. And we see approximately 85% of the time for temperature and 91% of the time for salinity that the upper 4 meters is well mixed. So this means the majority of the time what Aquarius sees and what a typical Argo float sees are about the same. However, these remaining time periods have some very unique processes in them. So shown here is data from float 6117, which was deployed north of Papua New Guinea in March of 2009. This is data from the primary SBE41 unit from 4 meters to 500 meters. We can see approximate annual cycle in warming with temperature and freshening in July due to rainfall, which is modulated by El Niño and La Niña events. Likewise, we can see the presence of barrier layers with the thermocline being deeper than the halocline. This white region here is when we actually changed the float mission to operate only in the upper 150 meters for a 3-week time period. So shown here is data from that 3-week time period in June and July of 2009. Looking at data from the STS unit for the upper 10 meters, we can see a clear diurnal cycle and temperature indicated by the striations and coloration. We also see approximate diurnal cycling and salinity. The extent of this diurnal warming is primarily contained to the upper 5 meters. And likewise, we can see the effects of rainfall events with a freshening and cooling of the water column here and a freshening and warming of the water column at the end of the time period. So to get a better idea of just how large this is, we difference from 15 meters, the STS data at 10 centimeter intervals. We can see a warming of up to 2 degrees C in the upper meter of the water column, which quickly decays with depth, and likewise freshening of up to 2 PSU in the upper water column. So to kind of get a better feel for under what conditions Aquarius and Argo might be different, shown here is the difference from the surface in 4 meters versus wind speed from a local tow mooring at 0 degrees north, 165 east. We can see that above wind speeds of approximately 6 meters per second, there's pretty good agreement. So to further investigate this, computed here the composite mean anomalies for temperature in the top panel and salinity in the middle. At the bottom here, we have the co-located trim 3-hourly rainfall. The black line here is the mixed layer depth as calculated from a gradient criteria. Looking at the top panel for temperature, we can see a clear diurnal warming signal contained in just the uppermost meter of the ocean on the order of about 0.2 degrees C, which has a time lag response with depth. Looking at salinity and rainfall, we can see kind of a preferential rainfall at about 7 o'clock in the morning, which doesn't really correspond with the freshest time period during the day, but this is consistent with Cronin and McFadden's 1999 study, where we saw the destabilization of the water column during the nighttime kind of overcomes the stabilization effect due to rainfall. So shown here is the temperature, the amplitude of the temperature and salinity diurnal cycle. It's just the range of composite plots computed for the 7 floats which have completed a fast cycle. We see an amplitude of the diurnal cycle of up to 0.5 degrees C and 0.2 PSU, contained again to just the upper couple meters of the ocean. So now I kind of want to spend a couple of minutes just quickly showing some initial results from SPURS. As Ray mentioned, we deployed STS floats as part of this. Shown here are the location of all of the floats we deployed. We deployed 8 of them while in transit to and from the region. The first 2 were actually deployed in the path of Hurricane Leslie, so that should be something very interesting to look at later on. And the rest were deployed in half-degree grid around the 3 SPURS central moorings. Here, and then this is the current location of the float, so you can see that they're all tending to kind of curve to the right and south. So going back to the first plot I showed, this is the histogram of the STS surface minus 4 meters. For actually only 11 of these floats, unfortunately, we've had a couple that have a little bit larger errors than normal between the 2 sensors, so I've left them out of the preliminary analysis for right now. But we can see, especially for temperature, the percentage of floats that are within plus or minus 0.1 degrees C and 0.1 PSU is slightly lower in this region. It's likely, especially for temperature, that this is due to enhanced stability in the water column, so we get a larger diurnal warming cycle. So to kind of look at this further, again, these are the difference from STS minus STS 15 meters for the upper 15 in comparison to float 6117, which I showed before, and then the 11 STS floats. So we can see, looking at temperature, that we do see a larger warming in the upper couple meters of the water column, in this case up to 4 degrees C, where it was only up to about 3 in the tropical western Pacific. And obviously we see a smaller response in salinity, which is kind of expected in the slow precipitation regime. So shown here is similar to what I showed earlier with the tau data, so the difference from the surface and 4 meters for the 11 STS floats in comparison to the wind speed from the Hui central mooring in the SPURS location. And we again see that above wind speeds of about 6 meters per second that the upper water column is well mixed. So lastly, I wanted to show an comparison of Aquarius data with the SPURS floats. So I took the Aquarius daily level 3 mapped sea surface salinity, shown here as an example of one day on November 1st, and co-located it with the 11 Argo floats, and I did it on a daily basis. So this resulted in 78 profiles for comparison. So shown here is Aquarius minus STS for those time periods. On the top is the actual shallowest STS reading, so that's anywhere from a depth of about 10 centimeters below the ocean surface to 50 centimeters below the ocean surface. And on the bottom is comparison with the SBE-41, the primary sensor, which is at a depth of 4 meters. And we don't see a huge difference between the two. And the mean difference we see, like what other people have seen, that Aquarius is biased low in this region, with the mean probably being around about 0.5 PSU. So in conclusion, STS sensors added to Argo-type floats greatly enhance the high-resolution elevation of this near-surface layer. In general, there's little difference between the two. However, we do see differences of 0.1 degrees C and 0.1 PSU. We also see a strong diurnal cycle and temperature, which is primarily controlled by local radiation, and a weak diurnal cycle and salinity, which is primarily controlled by precipitation and localized mixing. The temperature differences are larger in the SPURS grid region, likely due to enhanced stability in the region. Likewise, we see salinity is biased low in the area. And that's all I have.
Thank you, Jesse. Any questions? Tony.
The largest bias of Aquarius and SMOS
Uh-huh.
with regard to Argo is in the eastern equatorial Pacific, 90 cc.
Uh-huh.
And most of the flow they analyze in the western part. So I wonder whether there's a plan to deploy some Argo flow in the area where you see the largest bias.
Currently, I don't believe that we have plans to put them that far east, but we do have some that are further east, like more in the central. So, yeah, it would be definitely interesting to take a closer look at those. And I'm in the process of trying to look at, all the STS data for the past year. So,
Any other questions? Okay, thanks, Jesse. All right, let me introduce the next speaker then. This is Ping Shi from NOAA. He's going to talk about NOAA in situ satellite blended analyses of sea surface salinity. That's called BASS. I'm sorry? Oh. Prototype algorithm and applications. So, 1 second. Ping, I'll get you set up here.
This is Ping Zi from NOAA Climate Prediction Center. This work is a joint effort between 3 NOAA units, which is NOAA Climate Prediction Center, NOAA NESDIS STAR, and NOAA NODC. And of course, we get helps from our colleagues with SMOS and Aquarius. What we're going to talk about is a new effort that is undergoing to develop a in situ satellite branded analysis of surface salinity. Oops. This one. Okay. Objective analysis of surface salinity, and we do that through branding the information from the in situ measurements as well as the retrievals from Aquarius, both Aquarius and small satellite passive microwave observations. Our target, our goal is that the NOAA branded analysis surface salinity, which we call BASS, B-A-S-S, will cover the entire global ocean at a 1 degree latitude longitude grid, and it was starting from at least January 2010 on a time resolution of monthly or final. We started with monthly time resolution, and we hope in the future the quantitative, when everything is done, the quantitative consistency, we will get some quantitative consistency of this analysis with in situ based analysis for long time period, so that people can use this from a climate perspective. Okay, so let me talking about some basics about algorithms and imports. And here we talk about the basic import that is used in this this development. Basically, there are 2 groups of imports. The first one is in situ data, which is grid box mean of sea surface salinity measurements from the original, from all available profiles. It's not gridded analysis. It's the original profiles that is averaged for each grid box by each grid box. And for this study, we average them on a monthly scale to get a monthly mean, and as part of requirements for the branded analysis, need some error index for each input, so that we need a number of profiles available for each grid box and for each month as an index of for the accuracy. And we also use a monthly climatology on 1 degree by 1 degree grid box as the first case in the analysis, and all the in-situ data are quality control provided by NODC. And the satellite retrievals from both SMOS and Aquarius. We use level 2 products that several previous presenters has already introduced in, and we integrated them into 1 degree by 1 degree grid box from their respective low resolutions. And we also use the number of pixels available in each monthly time period in the 1 degree grid box as the index of random error. When we developed, in the development of this prototype algorithm, we use a relatively kind of older version of the data, which is basically, I think the versions, whichever we can get around the time frame of March 2012. It's not the up-to-date version, but we hope everything work here still holds for the new version. As a matter of fact, we plan to do the reprocess. The basic branding strategy. So this is this is very similar to the objective analysis we have developed for the SST and for the precipitation. Basically, it is a two-step approach. First, we try to remove the bias in the satellite retrievals of sea surface salinity, and several previous presenters have already mentioned the existence of those bias and potential impacts to their work. And as the first part of this work, we try to remove that. And the second part is to brand the in-situ measurements with the bias collected satellite retrievals. The bias collection part, what we do is that we basically establish we use localized PDF matching techniques. What we do is that we collect the collocated satellite retrieval data and the in-situ data, and then we establish localized PDF tables, and we match the PDF tables for the satellite retrievals against that for the in-situ data to collect the bias, so that the result of this bias collected satellite retrieval is that not only the mean values match with the in-situ measurements, but also the PDF of the sea surface salinity intensity also matches with the in-situ measurements. Then the blending procedure, second step, we take the OI approach, in which the first case is the analysis for the previous time steps, and the observation is the in-situ data and the satellite retrievals. And this is a example of the bias collection results. The left panels are for the SMOS. The right is for the Aquarius. From this view, and it's very hard to for me to see. But what you can find is that this is for, I think, for October 2011. Look at these the distributions of low sea surface salinity retrievals from two satellites. You can see the differences there. And one important thing here is that, at least for that version, the SMOS show a kind of artificial features along the coast here, and also show a strong kind of a band of salinity over here. And the bottom one, the bottom figures shows the bias collected one. The two of them very similar. Also, you can see these kind of artificial things are gone because we did a localized bias collection. Majority of these the distribution is collected as part of the bias. And this is a result for the mean distributions for 6 months from September to February. That was pretty much the whole data period that we could get around the March-April time frame. What you can find is the top is the salinity distributions that we get from the NODC in-situ based, and the middle is the bias collected SMOS. The bottom is bias collected Aquarius. What you can see is that you look at the 6 months mean from the 3 different sources. Now, the mean distributions are very similar. This is the cross-validation results for the bias collections. So basically what we do is that we will, each time we withdraw 10% of random selected in-situ data, and then we use the remaining 90% of the data to do the bias collection, repeat that by 10 times, and then we compare the bias collected results and the low satellite retrievals against the withdrawn in-situ measurements. What you can find is that, well, this line shows the results for the bias, relative random error, and the correlation. What you can find is that, well, of course, after the bias collection, the bias in the low salinity retrievals are gone largely. And the correlation is also improved. Correlation, you can compare this, you can see correlation is also improved. And this shows an example of the PDF distributions for the SMOS. The top panel, x-axis shows the salinity intensity, y-axis shows the frequency. The black line is those based on the in-situ data, and the red line is based on the low SMOS retrievals, and the green line is after bias collection. What we can find is that even if overall the low SMOS retrieval do not have a large bias, but if you look very carefully at the PDF structure, you can see the PDF structure is quite different compared to the in-situ data. But after the bias collection, not only the mean value, the mean bias is gone, but also the PDF structure matches very closely. And this is the same thing, but this time for the Aquarians, you can see also after the bias collection, the PDF for the bias collected the Aquarians matches closely with the in-situ data. And the OI is straightforward. We put in the observations. Of course, we need to define the errors for each individual input. And what's showing this is an example of the blended sea surface salinity analysis of the entire globe. And this is for October of 2011. You can see, well, a lot of fine structure that is presented here. As a part of the OI procedures, we can also give out the uncertainty estimations appears as estimated random error, since as part of the OI procedures, we need to put in the error estimation for each individual inputs. So that I think in the future, when user uses these products, they can have some ideas how accurate or how wrong the analysis is. This is the comparison between the top. The top is the straightforward in-situ-based analysis of salinity that is produced by NOAA. This is in-situ data only. The bottom is our prototype blended analysis. What you can see is that, first of all, the overall structure is this is for October 2011. First of all, the overall structure is very similar. You see those patterns were positive and negative anomaly patterns, especially over the Pacific Ocean, largely associated with the freshwater flux. But meanwhile, if you compare the in-situ only analysis and the blended analysis, what you can find is that the blended analysis gives us a lot of details. Of course, we need to do more work to demonstrate to what extent these details are true, to what extent these features are kind of artificial. But from the patterns, from some brief comparisons with the precipitation anomalies, we believe the majority of these stuffs are true signals. This is my last slide. Basically, we have developed the prototype algorithm, and we will repeat this process with the up-to-date version of both of SMOS and in-situ data to produce the blended analysis for 3-year period from 2010 to the end of this year, and perform more thorough examinations of the quantitative accuracy of this. And once, if we found that everything is okay, we want to try to take advantage of this as part of the real-time monitoring package. Thank you very much.
All right, any questions for Ping Ping? Okay, very nice presentation, thank you. All right, now the next presentation is another invited presentation from Nicolas Raoul from France, but he unfortunately could not make the journey here this week, so Jacqueline Poutin has agreed to give his presentation.
So this presentation is about the new vision, the SMOS satellite and then the Aquarius satellite provides about the tropical cyclone. So this work has been performed maybe mainly by IFREMER, CLS peoples, the Aquarius team, and also people at l'Océan Laboratory. So it is well known using historical surface properties that in the Amazon and Orinoco plumes, the sea surface temperature is very warm and warmer by more than 1 degree C with the surrounding open ocean during the hurricane season. In addition, it has been observed that the hurricanes passing the Amazon Orinoco plumes are usually of a higher category than the hurricane passing outside the Amazon plume. You can see the difference in statistics here. So the question is whether this plume has a role in the development of the hurricane. So first, the concentrate of the Hurricane Igor in September 2010. You can see the trajectory of the cyclone here. And they present here the pre-storms conditions. In particular here, you can see the sea surface temperature map. And superimposed on this map, the freshwater plume, the dark line, the black line here, indicates the freshwater plume as deduced from SMOS salinities. The intensification of the tropical cyclone starts over waters warmer than 28 degrees, and in that case you can see that the plume water was 29 degrees, so really the conditions are favorable for hurricane intensification over the plume. So they look also at the speed of the cyclone, and this cyclone slowed down as it traveled the Amazon plume. Then they looked at the atmospheric forcing. Here they plotted the maximum wind speed along the hurricane track, and you can see that the maximum speed was close to the plume, and it remains very large within the plume here. Oh, sorry, here. And from this, they compute a wind power index as suggested by Emmanuel Vincent, which is a proxy for the wind energy input to the ocean, and it is derived from an integral over time of the third square of the wind speed. And so you can see that this wind power index is maximum within the river plume. So there is the strongest atmospheric forcing over the river plume. Then looking at the salinity before the tropical cyclone and after the tropical cyclone, these are two SMOS salinity maps showing very clearly that the freshwater plumes, the extension of the freshwater plume decreased. And it was concentrated westward of the tropical cyclone after the passage of the tropical cyclone. So this concerns quite large areas over the ocean, and then they look at the mechanisms that could explain this. And first, they could explain this, yes. So here they look at the change after minus before the passage of the Amazon plume, the change in SST here, in salinity, and the deduced change in density, and here also they illustrate the change in CDOM. So you can see a cooling of the sea surface temperature starting close to the Amazon plume. And concerning the sea surface salinity increases just between the extension of the Amazon plume and the tropical cyclone trajectory. Concerning the altimetry, there's also a nice correlation between the change in altimetry and the wind power index. So then they compare the SMOS salinity and satellite temperature with Argo measurements taken on several parts along the tropical trajectory. And here it is a comparison between the salinity change as measured by SMOS and the one measured by Argo. You see a nice, quite nice correlation. The RMS error is 0.35, which is relatively small compared to the changes that are observed. And you see also the good correlation in temperature. So then, they look at the vertical profiles of temperature and salinity on several places, on 4 places. And so in these plots, the salinity is plotted in blue, and the temperature is plotted in black. The pre-storm conditions are plotted with a filled circle, and the post-storm conditions are plotted with open circle. I will start with the profiles that is measured within the Amazon plume, which remains in the parts of the plume that remains after the passage of the cyclone. It was characterized by a thick barrier layer, a more than 20-meter barrier layer, which suppressed the exchange between this water and the surface water. And you can see that after the tropical cyclone passage, the barrier layer is still there, and it is the reason why the temperature remains very warm and the salinity did not change much. In other parts of the plumes, here and there, before the cyclone arrives, there was also a barrier layer that you can see here, but which was much thinner and which was destroyed by the passage of the cyclone. In this other location here, there was almost no stratification in salinity, and the cooling appears because of deepening of the temperature mixed layer. So they look in more detail from satellite data on the cooling effect in the open ocean and in the plume waters as a function of the wind power index. And if you look at these graphs, you see here the evolution of the SST in the open ocean and in the plume waters. And you can see that for a moderate wind power index, you see that the evolution is very different because of the presence of the barrier layer. Then they wanted to look to see if what they saw on this particular example was representative on other historical cyclones. So they came back to all the cyclones measured during these time periods. And in fact, they look at the cyclones between over the period of the TMI MSR microwave satellite SST that they use to monitor the sea surface cooling amplitude in the wake of 190 storms. And they look at this cooling as a function of various parameters. So this is an example of Hurricane Ivan in 2004. you see here the speed of the cyclone, and that time the speed of the cyclone increases when it crosses the Amazon plume. But even if it was different from the Igor hurricane, the cooling in the plume waters that are shown in blue here was smaller than the cooling observed over the open ocean. And when compiling all the storms, you have here the cooling for slow storms and here for fast storms. They always observe that over the open ocean, the cooling was stronger than over the plume waters, very likely due to the barrier layer effect. After that study, they also work with the Aquarius team looking at the Hurricane Katia, and they end up with this SMOS salinity and Aquarius salinity around the Hurricane Katia, and showing again this very large salinity change, both seen on Aquarius and also SMOS after the passage of the hurricane, and this will be more detailed in the next presentation. So, in conclusion, the new sea surface salinity products from space can be used to improve the understanding of the processes involved in the oceanic response to tropical cyclone, and I would add to better understanding of processes at play in the surface ocean. They first evidenced the salinity changes in the wake of the tropical cyclone from spaceborne data. And in combination with sea surface temperatures, they provide a new vision of the change in density. The salt-driven stratification in the Amazon plume appears to be the processes that reduce the cooling by the wind-induced mixing, and this creates a potential for the tropical cyclone intensification. And next, they show that the SMOS salinity, but also the Aquarius salinity, can be used to better characterize the ocean potential variability in barrier layers areas, and this can be help improving the tropical cyclone intensification forecast.
Thank you very much, Jacqueline, for filling in. Are there any questions for this presentation? Okay, we'll move on then to the next presentation is on the same theme of the effect of hurricane passages over the Amazon plume. This is going to be given by Jim Carton. Mixed layer impact of Hurricane Katia passing over the Amazon Orinoco plume is viewed in remotely sent salinity observations.
Is there a mouse here? Okay, so this is very much a follow-on to the presentation you just saw just a moment ago. We'll be looking at the 2011 hurricane season. The first major storm you can see right now, that's Hurricane Irene, actually reached Category 3. It was Category 1 by the time it hit the East Coast. That was in mid-August. In late August, beginning of September, you can see Hurricane Katia. Hurricane Katia, actually, you'll see the eye in just a moment, turned into a Category 4 hurricane at maximum, and we'll focus on Hurricane Katia. So this is the track of Hurricane Katia. It's another one of these Cape Verde hurricanes, so it forms off West Africa in late August. It sweeps north and westward across the tropical Atlantic and catches the northern edge of the Amazon plume, which is kind of indicated in schematic there by that gray line. And we'll be interested in looking at the ocean response to Katia. So I'll begin by showing you some comparisons between the satellite remote sense data and in situ data. So you've already seen a number of these comparisons. This is a comparison of Aquarius sea surface salinity. This is version 1.3 versus tropical mooring salinity in both the Pacific and the Atlantic, and actually the Indian Ocean as well. And you can see that there's actually quite an empirical bi-monthly bias has been removed from the sea surface salinity data. And you can see actually quite good agreement. If you look along the dash line near the upper right-hand corner of the picture, you can see there's a slight negative bias. That's what several of the speakers have mentioned before. And if you look at the histogram, you can see that negative bias as well as an extension of the left-hand tail of the distribution. Of course, we're using the word bias. In fact, this may actually simply be a physical difference between salinity at the level at which the moorings are making the measurement and the measurements that the satellite are seeing. I'll show one more comparison. This is a comparison from one of the French ship of opportunity cruises made between South America and Europe. And this is the vessel Calibri. The colors that you see there are actually the salinities as observed by the ship. This is actually a little bit after Katia, and you can see in the region where there's blue as Calibri passes through the Amazon plume. And I've superimposed here time series. So the black line is actually salinities, these thermosalinograph salinities that you see aboard the ship, and the red and blue curves show the salinities as observed by SMOS and Aquarius, and you can see they overlap very well. The only real significant differences you see is when the satellites get very close to the coast of South America. And last thing I'm going to tell you about is the ocean response to Katia. So you saw this picture just a moment ago. So the dash line shows the track of Katia as it passes over the Amazon plume. The panel on the left, Aquarius, panel on the right, SMOS. Again, qualitatively, the results from the two instruments look very similar. And then, so if we take the difference in salinity between after passage and before passage for the two instruments separate, and we color those differences, regions which are red are regions where the salinities have increased, regions which are blue are regions where the salinity has decreased, and you can see that this northern plume northern extension of the Amazon plume has increased salinity significantly. The black line shows the 35 PSU contour. So you can see that as the hurricane passes over the Amazon plume, it's mixed up the high salinity water down below the plume. And this is a similar picture, only showing the change in sea surface temperature. Again, you can see in the wake of Hurricane Katia, the water column, because of mixing of the water column, you get decreased surface temperature, but the decrease in surface temperature is notably less pronounced as the hurricane passes over the plume, and then becomes much more pronounced if you look towards the upper left-hand part of the panels. The change in surface temperature is much more pronounced once it gets outside the plume. The panel on the left shows results from AVHR, remote sensing. Panel on the right is microwave TMI. And so that brings us to our simple idea of what's going on here. We think that basically as Hurricane Katia passes over the plume, mixing is occurring locally. If there were no barrier layer, then if we assume that the processes are adiabatic. We can easily calculate the change in surface temperature as a function of the deepening of the mix layer, so that the area of the box defined by the dashed line to the left and the solid line to the right within the mix layer itself has to be the same as the area of the box caused by the deepening of the mix layer. And of course, in the presence of a barrier layer, the situation changes dramatically, so that now if the barrier layer is contained within the mix layer and the mixing induced by the hurricane does not actually stir down below the depth of the temperature, bottom of the temperature-based mix layer, then the change in temperature of the mix layer would be 0. So let's take a look again at the passage of Katia over the plume. This is a close-up of the plume. The solid line shows the contour, 35 PSU contour before the passage, dashed line 35 PSU after passage, and we happen to have several Argo floats in this location, and I will show you what the Argo floats look like at 2 locations, indicated by the 2 black dots there. One black dot which is in the plume. That'll help. Thanks. So one black dot which is in the plume, and I'll take a look at also a profile outside the plume. And so these are the two profiles very near each other within the plume before and after the passage of Katia, and as you just saw in Jacques Lewin's presentation, there's a dramatic increase in salinity near surface and a relatively weak decrease in temperature when you're actually inside the plume. We can contrast the situation to what happens when you're outside the plume. Outside the plume, there's almost a uniform salinity in the vertical. The mix layer is entirely determined by temperature, and you see the classic response of the mix layer with this decrease of temperature by, in this case, about 1 degree C. And so the responses of the upper ocean are dramatically different depending on whether you're inside the Amazon plume or outside the Amazon plume. And then just if you look at sea surface salinity, sea surface temperature along the track, this is really just conveying the same information. So the vertical axis is time, horizontal axis is the longitude along track, and panel on the left shows sea surface salinity, panel on the right SST, and you can see that when you're outside the plume is this central region right here. So this is the plume right in here. Outside the plume, surface salinity cools dramatically. Inside the plume, the reduction in surface salinity, surface temperature, is much less pronounced. So to summarize, I've shown you comparisons of Aquarius to both in situ observations, these tropical moorings in the 3 basins, and also to SMOS. Agreement is very good. We do see this a slight bias of, we find to be about 0.1 PSU. We find an RMS difference on the order of about 0.4 PSU versus the tropical moorings. Again, this is version 1.3, and these are daily comparisons. We looked at the same phenomenon in both Aquarius and SMOS. The agreement's quite good, except when you get very near the coast. We've also taken a look at the impact on the barrier layer for Katia. You see this very substantial increase in salinity after the passage of Katia, and corresponding reduction in the amount of cooling, so that after the passage of Katia, the surface temperature only decreases by about 0.5 degrees. instead of 1 degree or more when you're outside. And thank you very much.
All right, any questions? Okay. Oh, one over here. Yeah, hey.
Do you have to worry about heat exchange? I mean, the hurricane's drawing a lot of heat out of the ocean, a lot of latent heat. It seems like you're only worrying about the mixing due to the hurricane and not the air-sea fluxes.
Right.
And how does that impact
Why don't you repeat the question, Jim?
Okay. Let me just show you this picture. So, as I understand Ray's question, when we were presenting this very simple model of the change in surface temperature due to mixing, we assumed that the processes were essentially adiabatic, so there was no flux of heat through the surface, so any cooling of the mix layer had to be balanced by a deepening of the mix layer, in other words, bringing up cool water from below. Actually, if you take a look at these profiles on the left-hand side, the story I've given you right now is not quite consistent with what you're looking at here, because you don't actually see that much deepening of the base of the mix layer, but you see this reduction in the temperature of the mix layer. So, in fact, what Ray is suggesting may be playing a very important role here. In other words, you may be actually fluxing heat out through the surface, and that's causing a significant fraction of the cooling of the mix layer rather than simply this adiabatic process. So you may be right.
Any other questions? All right, thank you very much, Jim. All right, now let me introduce the next talk. This is by Tony Lee, and this is another one of the talks that relates to the presentation I made this morning, where I highlighted some early results. This is on how Aquarius reveals salinity structure of tropical instability waves. It's by Tony Lee and a number of co-authors. Okay, Tony?
Thank you, Gary.
I'll get you set up here in a second.
Yep. Thanks. So this work is in collaboration with several scientists from JPL and Earth and Space Research, including Aquarius PI, Gary Lagloff, and project scientist Simon Yue, as well as Michelle Gerak and Sungying Gao and Catherine Dohan. And the work is motivated by early images of Aquarius, such as the one shown here, which was published in an EORS article and BAM's article, The State of the Climate in 2011, published by Gary and others. So the lower image shows a domain from about 2 north to about 20 north in the eastern tropical Pacific. And you see that in the lower part of the southern part of the image, you see this wiggling of the currents, as well as vortices. Which prompted us to look closer into the equatorial zone and identify the tropical instability wave. Now, tropical instability waves are 1,000-kilometer waves propagating towards the west in the Pacific and Atlantic Oceans, and they interact with the mean state of the ocean, both in the kinetic energy sense and the available potential energy sense, and they affect the climate variability and biogeochemistry. So they are very important features in the oceans. And Aquarius, for the first time from space, is able to capture these waves and also add to the understanding of the salinity characteristic of this wave, as I will describe in these presentations. And the results are published in an article in GRL at the 1-year anniversary of Aquarius. So now here in the figure, the color shading shows the salinity structure in December 2011. And the contour shows the temperature from quarter-degree Reynolds SST product. In the lower plot, the vectors here shows the surface current from the ASCA current product. So you see that there's a very coherent variation between temperature and salinity associated with those waves. In fact, you even see that you can identify the cups of those waves both in temperature and salinity data. And in the lower plot, you can see that these vortices called tropical instability vortices. And as it looped around, it basically pushed the salty South Pacific water to the north, and it pulled the fresher water from under the ITCC towards the south, and it does regulate this waveform. And but by no means I imply that this wave pattern here is only regulated by horizontal advection, because I believe that the vertical advection and mixing are also very important for the maintenance of this wave, as they do for SST associated with TIWs. So it's all nice that the Aquarius can capture the wave pattern, but after all, TIW have been observed for 3.5 decades, so especially by SST, and also by 2 decades of satellite altimetries, and as well as 2 decades of scatterometer wind data, as well as ocean color. So is there any value added by Aquarius in studying, monitoring, and understanding the behavior of this wave? So let's take a look at the propagation characteristics of this wave. So here I'm showing the longitude and time homolog diagram of the anomaly of salinity in the upper row, SST in the middle, and sea surface high anomaly in the lower. And to the left column shows the space-time diagram for the equator. The middle one is at 2 north, and the right column is for 4 north. So immediately you see that the SSS, SST, and SSH are best for observing this wave at different latitudes. And in fact, the salinity signal is the strongest at the equator, whereas the SST signal is the strongest near 2 north, whereas for altimeter data, it's the strongest near 4 north, and that's the standard latitude of the tropical instability vortices. So you see a very large response in the altimeter data. So I want to make 2 points with regard to this slide. So point number 1 is that the different satellite sensors are complementary to observing different aspects of the TIW. As I just pointed out, that the SSS, SST, and SSH are best for observing waves at different latitudes. And so the second point I would like to make is with regard to the propagation speed. Now there are 2 lines shown here, the solid line and the dashed line. The dashed line is correspond to 0.5 meter per second, which is the propagation speed of dominant TIW reported consistently by 3.5 decades of literature. The solid line is 1 meter per second, and it's actually described the propagation of the TIW at the equator very well. And as you go to higher latitudes, 2 and 4 north, you see that the dominant propagation speed become 0.5 meter per second, which is what was reported by decades of literatures. So I will explain these 2 points in the next few slides. So the first point is that why is that the salinity variability associated with TIW is larger near the equator than SST? Well, apparently that's because the meridional gradient of SST is the largest near the cold near the northern edge of the cold tongues, say near 2 north, whereas the largest meridional gradient of salinity is the largest near the equator, where the salty South Pacific water meets the fresher water under the intertropical convergence zone. So that's why near the equator, salinity actually provide better measurements of tropical instability wave. And in fact, if you take the random SST data and Aquarius data, you could actually quantify that the gradient at the equator for salinity is twice as large as SST, and vice versa if you go to 2 north. So these actually have very important implications. Now, there have been studies showing that the instability mechanism, meaning that the energy transfer between eddy or TIW and the mean flow are different at different latitudes, whether it's from mean kinetic to eddy potential and or eddy kinetic to the mean kinetic energies. So here at the equator, the fact that the salinity variability is substantially larger than the temperature variability means that the density variation associated with TIW and thus the eddy mean flow interaction is more controlled by salinity, not by temperature. And in fact, Semyon-Grosky has a paper a few years ago using Parata data for the tropical Atlantic, showing that the baroclinic energy transfer, when you account for the salinity, is actually larger by the temperature effect by about 5 times, very substantial. So here I would like to discuss another point, which is the faster propagation of the TIW near the equator. Now, as I mentioned before, that 3.5 decades of literature has been consistently reporting a 0.5 meter per second propagation, and that's primarily because most of the observations are based on SST and SSH. And as you see earlier, that the signal of SST and SSH propagation at the equator is very incoherent, and the best propagation is provided by the SSSS. So at first, I thought that, well, the difference between propagation speed on and off the equator is probably just reflecting different advection by the equatorial mean current. As it turns out, that further analysis of the data in different frequency band rejected that hypothesis. And it turns out that it has to do with two different types of tropical instability wave at two different periods. And in fact, there was a paper by John Lyman a few years ago analyzing the subsurface tow mooring data. And he was able to identify two distinct bands of TIW at 17 days and 33 days. Near the equator, the 17-day TIW is dominant. And away from the equator, the 33-day TIWs are dominant. And the 17-day TIW are actually associated with the Yanai wave type or mixed Rossby and gravity wave type, whereas the 33-day TIW is more like the Rossby wave type. So the physics are different. And so let's take a look at the Aquarius data and SST and SSH data associated with two frequency band. And shown here on the left is the total SSS, ST, and SSH anomaly. In the middle and the right-hand side, I show the same distribution, but for the 33-day band and the 17-day band. And as you can see that at the 33-day band, even at the equator, you can see that the propagation speed is indeed 0.5 meter per second. But if you look at the 17-day band, it's quite clear that it is dominated by the 1 meter per second propagation. So this is again showing that has nothing to do with advection. It's just the nature of the different bands of TIWs. Now, if you go to true north, again, you see that the 33-day band, 0.5 meter per second, and then the 17-day band, it's 1 meter per second. Same story for 4 north. So to sum up, the Aquarius review TIW salinity structure for the first time from space, and in fact, a large-scale propagation pattern. This is the actually the first observation from any observing system at all. Now, mooring data were able to show the period, but it has not been able to show these large-scale propagation patterns. And the Aquarius observation is therefore complement other satellite observations, SST and altimeter data, as well as with in situ data in studying the TIWs. And the TIW signal is stronger near the equator than SST. And so indicating that the salinity effect is more dominating in terms of the eddy mean flow interaction associated with TIW. And the dominant TIW speed at the equator is 1 meter per second, which is twice as large as the 0.5 meter per second speed reported consistently by decades of literature. And that is associated with different frequency band of TIW, because the 17-day TIW, which is associated with the Yanai wave or mixed gravity, Rossby gravity wave, is dominating at the equator, whereas the 33-day TIW, which is associated with the Rossby type waves, is more dominating off the equator, and that accounts for this difference in dominant speed and explain the Aquarius observation. I'll stop here. Thank you.
All right, any questions for Tony? Looks like you convinced them. Yes.
Thank you.
All right. All right, we have one final presentation, still in the theme of tropical Pacific dynamics, but now we look at longer timescales. This is a talk on the ENSO signature and the SMOS sea surface salinity maps. The paper will be presented by Jordi Font.
Good. Okay. Here again, now I will present work by Joaquim Valabrera that unfortunately could not come here. So I will do my best in presenting this. So the idea is that is to make an analysis on the capability of SMOS data to track the signature of the El Niño phenomenon. So this is an introduction. I assume that everybody knows what ENSO is, the oscillation that occurs periodically in the tropical Pacific, and that for sure, as it has a very important societal impact, there is for many years now, the scientific community wants to make consistent forecasts as long as possible. So now we'll see what happens. Well, this is a well-known scheme of the normal conditions in the tropical Pacific, with the whirlpool on the west, upwelling on the east, and the corresponding atmospheric circulation. So when El Niño occurs, you know the warm waters also go to the east, the thermocline is deepened into the east, and a modification on the atmospheric circulation. And during the La Niña is the cold part of the oscillation. Cold waters proceed to the west, and the surface trade winds intensify. So what we have here is average of, I think, some 20 and something years of sea surface salinity from in situ measurements that was compiled some time ago by Thierry Delcroix. You see that there is an asymmetry in both hemispheres, while the minimum values are displaced to the north, and you see that the maximum of salinity is coincident with the area where we have the maximum of evaporation minus precipitation in the southern part. So this is the variability of these average values. We can see that the variability is, let's say, is maximum in the area of the western part where we have the whirlpool. Also, the maximum appears in the eastern coast of this part of the equatorial Pacific. So this is a representation along 15 years of the conditions. With the vertical is for sure time, and the horizontal is longitude. These are averages for the equatorial Pacific from 4 degrees north to 4 degrees south. And we have sea surface temperature, sea surface salinity, and sea surface height. This is to locate the occurrence of El Niño. You can see that for sure temperature is tracking the occurrence, the clear occurrence of El Niño as in the 82, 83. We have also the presence of La Niña, that is the cold part of the oscillation. And if we look at what is the relation of salinity with this temperature oscillations, we see that during the El Niño, we have negative anomalies of salinity in the western part of the equatorial Pacific. Sometimes we have also some anomaly in the eastern part. And just before El Niño, we have positive anomalies of salinity in the west. And for sure, this is also the same case when we have La Niña, an intense La Niña, like can see here in 89. We have also positive salinity anomalies on the west. And this is for sure is important because it has been demonstrated if there are some calculations of the heat content on the surface layer, if these salinity anomalies are not taken into account, there are important errors in these calculations. So what I'm presenting now is results from a paper that was done also by Joaquim Vallabrera and Tony Busalaki and others some time ago. The idea was to check what could be the impact of having sea surface salinity in the forecast of El Niño. So in this case, what we present here is they built a model from a multi-correlation of different variables. We have here salinity, SST, salinity, sea surface height, precipitation minus evaporation, and the components of the wind stress. Here are the anomalies of these variables are correlated with the El Niño 3 index. So we can see then where is the maximum correlation for the different variables, and this is for a time lag of just 0. It means that it's correlated, the index, with the simultaneous variables. And the idea is to identify what could be predictors of the occurrence of El Niño in these variables. The result that is presented here is that, for sure, sea surface salinity is the best predictor, and in these specific regions that are numbered here, labeled by A, B, C, D, is where we find the best correlation between the SST values and the El Niño 3 index. For sure, this is quite obvious that temperature should be the best predictor because the El Niño index is derived from sea surface temperature. But if we examine this with a time lag of 3 months, so we look at the variables 3 months in advance to the El Niño values, the El Niño 3 values, we see that where we obtain a best predictor is by using sea surface height. In this region that is indicated here is the one that provides the better forecast for the occurrence of El Niño 3 months in advance. And if we go further in time difference, so for 6 months in this case, but it has been also computed for 8 months and 12 months, we see that the 3 variables, temperature, salinity, and height, provide a contribution to this prediction that is, in fact, independent one from the other. So, in particular, salinity provides, can explain by salinity alone can explain up to, I think it's 36% of the variability of the El Niño index. 6 months in advance can be explained by this. But in any case, if we use the rest of variables, that is temperature and height, we can explain, I think it's a total of 50% of the variability. And if salinity is added to this, it goes up to near 60%. So it's clear that with this time lag, salinity is an important contribution for the forecast of El Niño. So what we have here is the evolution of this El Niño 3 index, where we clearly identify the warm phases and the cold phases for a period from 84, I think, to 2012 in this case, or yes, the beginning of 2012. And on the right, we have a zoom for the period where we have contemporaneous SMOS data. So it's clear that when SMOS was launched, by the end of 2009, we were in a El Niño phase, but after this, we have got almost just El Niño conditions. So, because you know that the SMOS commissioning phase ended in May 2010, so from then on, we are just observing La Niña conditions. And now I am presented here the kind of SMOS data that have been used in this analysis. We have level 3 and level 4 products. Level 3 are just the ones that I presented before, these Binet salinity maps, while level 4 is a product that is introducing information from sea surface temperature spatial structures to improve the resolution of sea surface salinity. Tomorrow you can see a poster with an explanation of these kind of products. So using this, and with a specific configuration that I will not detail here, we don't improve the bias, but we improve the noise quite significantly. So, if we average the 2 months of, September for the 2 years, 2010 and 2011, the sea surface salinity anomaly, and we compare this with the kind of structures that I showed before that was examined in this paper, we see that there is a consistency in the spatial patterns. in SMOS data compared to the anomalies when they were examined a long time ago for the month of December. And also, if we go to the 3 months previous to the peak of the event, that is an average of September, October, November, we see that there is also quite a good, let's say, coherence in the spatial structures. If we look now at the temporal evolution of the something similar to what I showed in a previous slide, here we have on the left, from in situ data, optimally interpolated, it goes from 2000 to 2012. And in the top, we have marked the part that is corresponding with the period of SMOS data. And in the other two panels, we see the SMOS level 3 BINET data, and on the right, the level 4. We can see for sure that using level 4, we have a much better identification of the oscillations, because we have reduced quite importantly the noise, and we observe an evolution that is quite consistent with what is seen in the in situ data. So if we examine the temporal variability of this, here we have monthly averages of SMOS data compared in this case to tau surface data in one precise location as indicated in the map. So what we can see is that in red we have the tau time evolution, in blue we have the SMOS BINET data, and in green we have the level 4 SMOS. We see that this temporal evolution that is observed in the in situ data can also be observed in the SMOS data, especially in the level 4 products. And if we compare this to climatology, that is the dashed black line, and also if we compare to the same location in situ data but for the previous year, it is evident that SMOS is able to track the temporal evolution in this location that can be used for sure to detect the presence of, for example, this freshening that is shown both in satellite and in situ data. In other locations, we have a different time evolution, but we can in general see that what is observed by SMOS, even noisy, is for sure with, let's say, an accuracy that could be better than what is the interannual variability. So it means that we can observe this kind of phenomena evolution. And this is for another location. We can see that the BINET data is much more noisier than the level 4, but level 4 follows quite well what is the in situ evolution. So just to finish, we see that we have been only in the La Niña phase during SMOS data, that the monthly averages show a signature of the anomalies that are consistent with the expected pattern obtained from during the La Niña. Then even with the level 3, we can observe this kind of oscillations quite consistently, and for sure the results are improved when we use the level 4 data. In any case, if you are interested in this kind of level 4 products, I repeat that tomorrow there will be a poster explaining this kind of methodology. Thank you very much.
Thank you. Any questions for Jordi? All right, I think everyone's ready for lunch. So this then brings to a close this morning's session. I want to thank all the speakers in both the early and the second parts of the presentations. I think we've seen some very interesting new results. This is kind of a flagship AGU session on these missions, and I'm sure we'll be back next year with a lot more to say about ocean salinity and ocean salinity dynamics. So again, thanks for everyone for being here, and to all the presenters.